So we have yi equals, and now what I'm going to say is it's alpha 0I plus x1I alpha 1I plus x2I alpha 2I plus x3I alpha, and I'll call it 3I plus epsilon I, where I'm now allowing the coefficients, each coefficient, to vary with I. Now again, this is saturated. This is over parameterized. If I could get estimates of those things, I'd have a horribly overfit model. So I do what I just suggested. Alpha 0I is equal to beta 0, 0 plus zi transpose beta 0. And you could throw an error on there. That error will end up in the larger error. Let's just forget that for the time being. And I have alpha 1I, same thing. It's going to be beta 1, 0, the intercept, plus zi transpose beta 1. All the way down, alpha 3I equals beta 3, 0 plus zi transpose beta 3. Okay? So let's take these equations and plug it into that top equation. And that's going to give me a yi equals beta 0, 0 plus zi transpose beta 0. Okay? So that means I'm going to have all the personal characteristics of the individual in there, all by themselves. Then I have plus x1I, and I'm going to have beta 1, 0 plus zi transpose beta 1. Let's look at this a little bit. This gives me a x1I beta 1, 0 plus x1 times each one of the z's. So I have the interaction between the first economic variable and each one of the socioeconomic variables. Okay? So x1 I times zi transpose beta 1. Okay. Well, let me get rid of that because I was just illustrating. Okay. Plus x2I beta 2, 0 plus zi transpose beta 2 plus x3I beta 3, 0 plus zi transpose beta 3 plus epsilon I. Okay. And this epsilon I really won't be the same as this epsilon I because there are really errors in over here. It's just a notation. But here's the point of all this. What I've done is I've set up a regression. Okay. Regress y on the z's right here. The x's, x1, beta 1, x2, beta 2, x3, beta 3. So the x's and all the interactions. And I'm going to write that as x, z. Okay. So x1 times z1, x2 times z1, x3 times z1, x1 times z2, x2 times z2, x3 times z3, z2. And I could keep doing that for as many z's as I have. Okay? So you regress y on the socioeconomic variables, the economic variables, and the interactions of the two. And that's how I handle heterogeneity. Now, this is not the only way, and it isn't necessarily even the best way, or I shouldn't say the best way. It may not handle the heterogeneity entirely. What does heterogeneity cause you in economics? Basically, it's an omitted variable problem. It means there's some variables sitting out here in the air that are going to bias you. So if we had just done y's on the z's without the economic variables or the interactions, we would have an omitted x variable of variables, and all the interactions are omitted. And if any of those are correlated with the z's and they're important, we're going to have an omitted variable bias. Similarly, if we just did it on the x's. Similarly, if we just did it on the z's and x's. Similarly, if we just did it on the interactions. Now, this brings up one other thing. When you have a model with linear terms, interactions, perhaps quadratic terms. I didn't put quadratic terms in here, but I could have. The linear terms are the lower order terms. The squares and the interactions are higher order terms. When you model, you don't ever simply model the higher terms and set the lower ones to 0 unless there's some principled way of doing that, unless you have some method for doing that. And we'll learn how to do that with the LASSO. Okay? This is a very, very, very general approach to modeling. It's one I use all the time, and it helps me think through first the economics, and then how the heterogeneity in people, the differences in people, will be reflected in the model. So I'm doing two parts of the modeling. You could just jump and say, okay, I have all these variables, include all the variables and all their interactions. That's fine too. I just find this a more useful way of thinking about things and for justifying why you would throw those interactions. Now, let me tell you a little bit more about this modeling method. That was a linear model. We have a logistic model. And remember, with the logistic model, and let's just do the simple binary logistic model. With the binary logistic model, we have log of pi 1 minus pi equals, I'll say, theta I. Okay? And then we said, well, we could have theta I a constant, so everybody's probability is the same. We could let it vary, but then we're not going to be able to get estimates. Or we can try and let theta I equal, we'll say, xi, I'll make it a beta. Okay. Now, the key thing I want to point out here is that log pi over 1 minus pi is log e of yi over 1 minus e of yi, okay, is a function G of E of yi. And I'll put a given X in there. Okay? Any model where G of E of y I given xi is equal to xi transpose beta, where I could have a beta 0 in here, is called a generalized linear model. Okay. And there are some restrictions on G. G has to be increasing monotonically, and it has to have some other features. But by and large, all of the models that you've ever seen in economics are probably generalized linear models. Other models, there's so-called Poisson models. Poisson models you use to handle count data. You know, how many items did you buy? You bought 0, 1, 2, 3, 4, etc. And there are other generalized linear models. My point here is that this method of starting with a really inflexible model, having a totally flexible model, and then modeling something in between that is flexible but not totally flexible, is an approach that you can use for all of these kinds of models. And you can do it in stages. You can say, well, first I'm going to model the economics. And then I'm going to say, well, not everybody's going to have the same reaction, even though their functional forms might be the same. And then I'm going to model how their coefficients change. And I like doing that because then you get the economics in there. You get the economics in there first, and then you say, different people behave differently. I don't like just throwing everything in there and say, well, you know, interactions have to matter, and now we're done. So let me continue this with this conditional logit model I was talking about last time. And I'm going to take a situation where I have 3 alternatives. Okay, so 3 alternatives. In people with characteristics Zi, and each alternative for each person has characteristics X, I, I'll call it X, K, N, K equals 1 through 1, 2, and 3, N equals 1 through N. Oftentimes, you'll find that the characteristics for each alternative for each person are the same, but will depend upon N. So, what are the characteristics of the Netflix movie? Let's say it's Braveheart. Well, those characteristics are the same for me, the same for you, the same for everybody else. And so if the alternatives of Braveheart are the same for everybody, then this set of alternatives doesn't vary with n. Now, what if it's the case that some people have to pay something different for watching that movie? Then it might be the case that one of the features differs, price. It might be the case that for something, all of the features differ. So you're buying a car, and with the car, you have the trim package you purchase, the prices of each component, whether you have leather seating or not, whether you have heated seating or not, whether or not you have tinted windows, whether or not you have a sunroof, and so on. And those would all be characteristics of the different cars. You also have the different brands of the cars. So in those cases, many or all of the economic characteristics would differ. Then we said each alternative for each person has an attractiveness. Okay. A, in this case, it would be K n. And we have the probability K is chosen by n equals AKN over A1n plus A2n plus A3n. So that's the Logit assumption. It has the problem of independence of irrelevant alternatives. It has the feature that I can easily add a alternative I haven't seen before. I'm going to get rid of these. And I recall that the attractiveness, AKN, was of the form EXP theta IN, where theta IN is the parameter, if you will, and I have actually that should be K. I have 3 times n of those, and there's no way within observations I can estimate the KNs. And so now we go to this method of estimation I was talking about, or modeling. We'll say, let's start with theta Kn equals theta. That is, everybody shares the same attractiveness. We could go a little further and say everybody has the same attractiveness, but they're different for different alternatives. But your attractiveness for a Ford of a certain type is exactly the same as mine for a Ford of a certain type, but we both have different preferences for a BMW, but your preferences for that BMW, my preference for those BMW is the same. Well, we don't really believe that either, right? And so we start with the economics first. Forget about the fact that we differ as people. We say those theta K may in fact depend upon the characteristics of the alternative. And so we're going to say first that theta k is equal to x k transpose beta. Okay. So notice here I don't have the x's varying, but I could do that very easily. Okay. I could say this is theta kn, and then this becomes xkn beta. And that gives us the conditional Logit model. Okay. That is that theta kn, which is the log of the attractiveness, is x transpose kn times beta. And the point here is these beta are constant. These beta are constant. So if I were to change the characteristics of a BMW, it would have the same reaction to me as it has to you, because our responses to changes in the characteristics are the same. Well, we typically don't believe that. I don't care about having seats that are warm in my car. I have family members who would rather die than get into a car in the wintertime when the seat isn't warm. And that being the case, I have to take care of that. How am I going to do that? Well, now I'm going to use the fact that we have characteristics of the individuals. I said I here, I switched to N. Sorry about that. So now what am I going to do? Okay. I'm going to say that theta kn is equal to x kn transpose beta. And now I'm going to let beta depend upon n. So I'm going to allow different people to have different betas. And if I try and estimate this model, this won't work. There are too many betas to estimate there, and it's simply not going to work. I'll either get an overfit model or I won't get an answer. I won't get an interpretable model. And so I go back and I say, okay, let's take a simple Bn equals beta 0 plus Zn transpose beta. Okay. Well, if I do that, then what do I get? I get that theta kn equals x kn transpose beta 0 plus, and I'm not going to write out what this is. I'm just going to say all the interactions between x, k, n, and Zn. So if there are 10 features in xkn and there are 20 features in Zn, I'll have 10 times 20 interactions in there. So this will be a very big, complicated model, but it's still going to be a logistic regression model. We also talked about the situation where we had the contraceptives. And in the contraceptive case, we didn't have any x's. Okay, we just had beta n's, and so we ended up with a model that let's see, we ended up with a model that simply had the characteristics of the woman, and we had that the betas differed alternative to alternative. So you're going to run into this a fair amount. Usually people will simply say, oh, we're going to have a big multinomial regression model. So they'll say something like this: we're going to have, I'll call it G of E of Y given X equals, I'll just say X transpose beta, where the X's have the economic variables, have the socio-demographic variables, have the interactions between them. Some of the betas will vary person to person, some of them will not. And these models can be, on the one hand, very complex, but as you will find, it's the modeling part of doing econometrics that's the hard part. It is not the estimation part. Once you have your model set up, you just go to your friendly computer and say, computer, I need to use this program to analyze those data that I've modeled in this way, that way, or the other way. And I'll have you do a homework with 3 examples of this for a week from this Wednesday. So this is all well and good. We'll talk more about interpretation, but I want to go back now to prediction. And you may remember that when we do prediction, we hang on a second, I'll be right back. Got a light flickering there. You may recall when we had prediction for classification models, we used the Bayes rule. And you remember how the Bayes rule works. The Bayes rule says that if the probability of a success is greater than 0.5, then we assign a person with that probability to the success class. If the failure class is greater than 0.5, we assign the person to the failure class. Or in a situation that's multi-class, we calculate all the probabilities and you get assigned to the class that has the highest probability for your characteristics. Okay, that's the Bayes classification rule. And what we can show is the Bayes classification rule has the minimum Bayes risk. It has the minimum error in the way we've been measuring errors. And everyone says, wow, you know, that's really good. This is really a great thing. And the problem is that it is not. Okay? And I'll give you some examples of this. And then we can talk about it some more. Let's first talk about what can go wrong, okay? So I'm going to give a table here, truth, and it can be a 0 or a 1. And I can have prediction. I'll write it P-R-E-D-I-C-T. predict, and predict can be a 0 or a 1. And I'll do this a couple of times in this lecture, because this is really important. What can go wrong here? Okay. Well, I can have a true negative. That is, if I predict 0 and the truth is 0, that is a true negative. Okay. If I predict 0, but the truth is 1, that's a false negative. Similarly, if I predict 1 and the truth is 0, that's a false positive. That is, I predicted, let's see, am I doing this wrong? I predicted it was 1. Yeah, I predicted it's a positive, and it was a negative. And finally, I have a true positive. That is, if I predict it's a 1 and it's a 1, then it's a true positive. Okay. Now, what are the mistakes I can make? I can have false positives and false negatives. I'm going to put this here. I'm going to call this n plus for the time being. And I'm going to call this, actually not n plus. I'm going to call this n0. And I'm going to call this n1. Okay. So these are the actual zeros, n0, n1 are the actual ones. Over here, I have the predicted. So here I have the predicted zeros, and I have the predicted ones, and here I have the total number of observations. Okay. It's called a confusion matrix. That is, I would actually have numbers in here, and I'm going to go and talk about this. What the Bayes rule does is it minimizes the sum of the false positives and the false negatives. Now, it turns out that's a problem. Because what it really says is that the harm from a false positive is the same as from a false negative. And we're going to have a number of examples here. But one example might be you're looking at giving loans. And you have defaulters and non-defaulters. And what's your loss if somebody defaults? Now let's say there's no collateral. Then you're out the loan, and you're out the any legal fees you tried to get it back. Let's say that you don't give somebody a loan that should have gotten a loan. What's the loss for doing that? Well, you're out the interest that you would have earned, which presumably isn't anywhere near what that principal was. So a false positive saying somebody's not going to be a defaulter when in fact they are is a much worse thing than saying somebody is going to be a defaulter when they're not, at least in terms of the effect on profits. Similarly, let's say that we're looking at whether you have cancer or not. And I say a false positive is you tested for cancer, and so we're sending you in for more tests, and there's a bunch of expense associated with that. On the other hand, there's a false negative. We say, okay, you're fine, go home, and then you die 6 months later from cancer. One would argue that the false negative there was much more serious than the false positive. Similarly, think of COVID, okay? Let's say you have a test to determine whether somebody had it or not, and if they had it, then you let them go back to work, okay? Now, if it turns out you have a false negative there, it says he didn't have it, and so he can't go back to work, you know, that's probably okay. On the other hand, if I send somebody back to work who hasn't had it and maybe has it and is asymptomatic, they could make everybody else sick. And so there's a asymmetry in the seriousness of making false positives and false negatives. And as I'll show at the end of the lecture, the Bayes rule essentially treats false positives and false negatives. For this part of the lecture, I'm going to continue with that, even though I don't do things that way. After I get done talking about what's in the book and how the book does it, I'll tell you how you ought to do it. And that's to use something called decision theory. And we'll get back into talking about utilities, which are great for economists, though, as I've said, oftentimes the statisticians wince when we do this. So let me give you the example from the book. And the example from the book, recall, was, let's see, is this? Yes. The example from the book was using LDA for determining whether somebody was a defaulter or not a defaulter. So you have your linear discriminant analysis, but it really doesn't matter how you got this. If you had this chart, you would have problems. Similarly, the book also points out that the chart is based on LDA on the test, on the training sample, not on the test sample. And that's a bad thing to do too. Again, it could be the case you got this from the test sample. And so let's just assume that's how it was gotten, even though it was not gotten, because the issue is going to be the same. So I have up here again true. Okay. And I have not defaulters and defaulters. Okay. And over here, I have predict. And I have not defaulters and defaulters. And in the example in the book, we had 9,644 non-defaulters who were correctly predicted as non-defaulters. We had 23 non-defaulters who were predicted as defaulters, so they didn't get loans. And that gave us 9,667 non-defaulters. So there were a total of 9,667 non-defaulters. There were people who were predicted not defaulters that were defaulters, and there were 252 of those. And we had 81 defaulters who were predicted as defaulters, so true, and that's 333, and this is 10,000, this is 104, and this is 9896. Now, the thing to notice is the misclassification rate is 23 plus 252 divided by 10,000, okay? So the misclassification rate is 23, that was wrong, 252 over 10,000, and that is around, what is it, 2 point something? 2.75%. You see, you know, that's not bad. That's not bad. I will ask you something. What if instead of doing all this statistical stuff, I said, you know, most people aren't going to default, and so I'm just going to give everyone a loan? You wouldn't do too much worse than this. You wouldn't do too much worse than this. Okay? Now, here's what the problem is. Well, let's do one good thing, another good thing, okay? I have the number that were actually correctly said to be non-defaulters over the number of non-defaulters, and that's pretty small. I also have the number of defaulters over the total number, and that's pretty small. That's about 3.3%. But here's the thing that's bad. This is really bad. How many defaulters did we have? We had 333. And how many did we miss? We missed 252 and 252 over 333. Whoops, let me not do it in red. $252 over 333, and that's equal to a 75.7 error rate. I missed 75% of the people who were going to default. Let's say that this has to do with testing for some incredibly virulent disease, and you know, with a very high R factor, and you're trying to keep people out of an area that have the disease. Okay, and even one person in there is bad. You know, think of Ebola. Think of COVID. Think of the Spanish flu of the turn of the previous century. And your job is to catch and quarantine the people who have this disease. And if your error rate was 75.7%, I think they would say you're not doing a very good job. You're not doing a very good job. So what we would really like to do is we would like to get this low without driving this true, I'll call it positive, this true non-defaulter rate without driving that down too much. Right? Now, I can always eliminate this error. How do I do that? I just say everybody is assumed to have the disease and we're going to quarantine them all. And so then we catch them all. Well, the problem is then we're having non-defaulters being classified as defaulters, or people who don't have the disease being classified as having the disease. So these class-specific errors, these class-specific rates are very, very, very important. And I hope you've written this down, because I don't want to write this up again. I will if I have to. I may at the end of the lecture. But I'd like to go and start talking about various components of this matrix. Now, recall that we said that y hat equals 1 if the probability y given, and do I want to have an x in there? Yes. X is greater than 0.5, but I'm now going to put a theta there. Okay? Because one response to this is to say, look, having a default's really serious, and I'm not willing to take a chance. And so if you don't have a 90% probability of being a non-defaulter, I'm just going to say you're a defaulter. Okay? So this is called a threshold. And what we're going to do is we're going to vary the threshold. I'm going to vary the threshold. I'm going to look at overall rates. I'm going to look at false negative rates. And for this example, I'm going to do the following. I'm going to have, this is 0.5. This is 0.6. And what I'm going to do is I'm going to start varying theta. So I'm going to start theta at 0. And I'm going to ask what happens with the false negative rates and the false positive rates. So if I start at 0, the false negative rates go something like that. So as I increase theta, the false negative rates increase. Let me get the other here. Similarly, if I start at 0, the false positive rate decreases. Okay. And finally, if I look at the overall rate, the Bayes rate, it looks something like this. This is overall. Okay. Okay. So to reduce the false negative rate, you might want to take theta to be 0.1. Okay. So if I take theta to be, let's see, that would be actually I'd want that to be 0.9 probably. Let's say I take y hat equals 1 as you're found to be a defaulter, not a found to be a defaulter, and basically I'm going to assign you to be a defaulter, even if it's somewhat unlikely you're a defaulter, just because it costs me so much. So, how do we measure whether or not our classification rule is doing a good thing now that I have this threshold in there? Okay. By the way, this begs the question of what the threshold is. And that's part of the problem here. We agree that the false negatives are worse than the false positives, or vice versa, depending on the situation. What should that threshold be? Well, that's what the latter part of the lecture is going to be about. So let me put up two new curves here. And then talk about some new terms that really are terms that you've seen before, just in different guises. We're going to talk about the ROC. Receiver operating characteristic curve. And it comes from signal processing. Some people just call it the receiver operating curve because they don't know. And some would just call it the ROC, and they have no idea what the RO and C mean. By the way, it's very bad to go in an interview and not know what the terms are. Even if you could describe what the ROC is, it's always good to say, oh yeah, it means that, and it came from this history. And you can find that out simply by going to Wikipedia. So over here, I'm going to put the true positive rate. And over here, I'm going to put the false positive rate. Okay. True positive rate can't be any greater than 1. False positive rate can't be any greater than 1. So I have a square there. Okay. And then what I'm going to do is I'm going to take theta and vary it. Okay. I'm going to take theta and I'm going to vary it. Recall that theta is our threshold. Okay. And I'm going to start with theta equals 0. And for theta equals 0, I can have, there is a, I'll put a 0 here. There is a true positive rate and a false positive rate. Okay. And then I could take theta equal to, say, 0.1, and I would get a true positive rate at 0.1 and a false positive rate at 0.1. And for any theta, I would get a TP at theta and an FP at theta. Okay? And finally, I would have theta equals 1, and I have a TP at 1 and an FP at 1. Okay? Well, these are pairs of points. Okay? And I have a pair of points for each possible theta, and so I can plot those one against the other, and oftentimes we will find that the relationship looks something like that. Okay. Okay. This is called the ROC curve. Okay. I start here with theta equals 0, and I move along here up to that point. Now, what people like is for this curve to hug the square. That is, let's say I have a different classification procedure. And its ROC looks like that. Then I would say that the classification procedure that gave me the red is better than the classification procedure that gave me the black. Let's say that I just picked at random. Okay? If I just pick at random, the ROC is going to be a straight 45-degree line. Okay, so this would be the worst situation. Something that went up here would be the best situation. And you would really like for that to look that way. Now, there's some problems with this I'll go into in a minute. But right now, I'm going to say people, while they look at the ROC, they don't want to have to graph things. And so what they do is they look at the areas under the curve. Okay, so the AUC equals the area under the ROC. Okay, and I want you to notice something. If you had a perfect predictor, what would the area under the ROC be? It would be equal to 1. You all see that? It would be all equal to 1. In contrast, if I have the worst possible, this would be equal to a half. So the ROC goes from a half to 1, with 1 being the best. Okay, so choose the procedure with biggest AUC. That's kind of hard to see, isn't it? So this is the 45-degree line. And this square dotted reddish thing is the almost perfect procedure. The AUC is very much like an R-squared. You want it close to 1. However, it has the problem that you don't know what the trade-off should be. You know, what theta should you take? Is there an optimal theta? So the class-specific performance is really important here. And so I'm going to go back and I'm going to put that confusion matrix back up again. And let's see, do I want to do this one? Or do I want to do this one? Yeah. So making a mid-course correction here. So I'm going to put that confusion curve back up, or confusion matrix back up. And we're going to define some terms, which, since I don't use them a whole lot, I always screw them up. So no, this isn't going to work. Theta be the threshold. Okay, just like we said before. Xn is predicted positive, I'll say positive, if probability y equals 1 given xn is greater than theta. Okay. And now I want to define some terms. Okay. The first thing I'm going to start with is so-called true positive. What's the true positive? That's the summation I equals 1 through n. Indicator function yi is equal to y hat I. Okay. Or I'm going to write it a different way. Yi equals 1 and y hat I equals 1. And I'm going to use the symbol and intersect there. So the prediction is 1 and that is 1. The equality was wrong because I forgot about the negatives. Okay. Define the false positive. Okay. That's the summation I equals 1 through n. It was equal to 0, but it was predicted as positive. So that's a false positive. Then we have true negatives. And what's the true negatives going to be? Well, that's going to be the summation I equals 1 through n, I, yi equals 0, and yi hat equals 0. So that's the number of times you predicted it was going to be negative or 0, and you ended up being correct. So we have true positives, false positives, true negatives. What's the other one that's left? False negatives. Summation I equals 1 through n. Okay. It's a false negative, so that means I predicted it was going to be 0. I mean, it was 0, and I predicted that it was, oops, other way around. I predicted it was going to be 0, and it in fact was equal to 1. Okay. So those are the 4 things we can look at, and I'm going to put those again back into a confusion matrix. And you will find that people order these confusion matrices in all different ways. So it's best if you learn how to set them up and label them correctly, because sometimes the positives will be on top, sometimes the negatives will be on top. I'm doing this just for 2 classes. You can do this for many classes. So let's take a look at the confusion matrix again.
Can I ask a question?
Sure.
The all the values for the false positive and the false negative, those are counterfactual. So is that just a theoretical concept?
No. There was you predicted. So this is in your say your training set. Okay. I mean your test set. Your model says you have cancer, and we find out you don't have cancer. Okay. And so those are not theoretical. Those are actual. And so what we're going to want to be able to do is we're going to want to find some way from our training data to make sure our tests are doing the right thing. That is, we're getting the correct trade-off, the correct threshold. And in fact, it's going to turn out not really to be a threshold, as you will see, although you can put it that way. So I'm going to put y up here. I'm going to put y hat here. I'm going to put do I want 0 and 1? Yeah, 0 and 1 here, 0 and 1 there, and extend these over here. Okay. And so if I predict 0 and I get a 0, that's a true negative. Okay. If I predict 0 and I get a positive, that is a false negative. If I predict positive and it turns out to be 0, that's going to be a false negative. And if I predict positive and I get positive, that's going to be a true positive. And what I'm going to have here now are the number of negatives. I'm going to have over here the number of actual positives. Here, I'm going to have the predicted number of negatives, negatives. And here I have the predicted number of positives, and here is my total. Okay. And these numbers you would find out by doing your job, predicting these people should get loans, and some of them default, and your manager coming to you and say, what were you doing for the last 6 months? You know, you missed all the defaulters. And you say, well, I got, you know, all the people who weren't going to default. And he goes, my kid could have done that. He just would have let everybody come in and say, you look like a nice person, you get a loan. And he or she would have done just about as well as you did. And so depending on what your classification rule is, these are going to be real numbers. And what you want to do is you want to trade them off somehow to give you the right answer. Now, here's some definitions. And you have to commit these to memory because, frankly, nobody will believe you took a machine learning course if you don't know these terms. And depending upon whether you're talking to a systems engineer, a software development engineer, a machine learning scientist, a statistician, they're going to call them different things. The first thing we're going to talk about is the precision. And the precision is the true positives over p hat. Okay? It's the true positives over the total number of positives. Okay? You'd like that to be very high. This is also called the positive predictive proportion. I've actually never used that term, and I've never been around anyone who has. But it's called the value, pardon me, not proportion, value. I knew something was wrong there. P, E, B. Okay? So that's the first definition, precision. It is this divided by that. The second we're interested in is specificity. Okay? And the specificity is the true negatives divided by the total number of negatives. Okay? So it is Tn divided by n. And you would like that number to be pretty large too. This is also equal to 1 minus the false positive rate. And we'll look at that some more in a minute. Yeah, I'm gonna have to erase this matrix here. You have it in your notes, so you can refer back to it. Okay. What's the false positive rate? Okay. Well, this has a bunch of different names. Okay. It's false acceptance. Okay. And here's something you will all like. This is the type 1 error rate. Remember that? And so you might be sitting there saying, well, if there's a type 1 error rate, there must be a type 2 error rate, and power must enter in here somehow. And the answer is yes. All these things are all related to those things that you learned before. This is false positives over n. Okay. And it's equal to 1 minus the specificity. It's 1 minus this. So these two are equal. Okay. And then there's one other that we don't use very often, but I'm putting it in here because I mentioned the type 1 error rate, and I'm going to have to erase precision. And that's the false negative rate. Okay. This is equal to false rejections. And if you think about null alternatives and the like, this is also equal to the type 2, type 2 error rate. Okay. It's Fn over P, and it's 1 minus the TPR. Okay. And you may recall that the power is 1 minus that. That is, it's the probability that you correctly reject a false hypothesis. Let's see, do I want to do this? Yes, I do. So you will see these terms pop up, and people use them like they use mean square error or R squared or significance and p-values. And depending on how you were trained, somebody's going to go, well, you know, your precision and recall here, you know, I'm not real comfortable with that. Or I'm not real happy about your false positive rate. Or I'm not real happy with your false negative rate. Or, you know, your specificity is really off here. Did I talk about sensitivity? I think I did. But you'll see precision and recall a lot, so I'm going to go a little bit more into this, reminding you that once we've gone through all this and you've learned it so that when you're in an interview, you can spout this stuff off, and then you can say, you know, there's a real problem with this stuff. And the problem with this stuff, and I'll reiterate it again, is it essentially treats it doesn't in any principled way trade off false positives and false negatives. Okay. It does have a threshold in there, and then somebody goes, yeah, I think 0.9 seems fine. And whenever somebody says that, I go, so why not 0.895? And if they agree with that, then I'll say, well, then why not 0.91? And they'll agree with that, and I'll say, well, then why not 0.8? Oh, that's too small. Well, how about 0.83? Yeah, I think that's okay. And you sit there and you say, look, they're just pulling things right out of the air. And that isn't the right way to go about making these decisions. What are these decisions? You're giving people loans, you're not giving them loans. You're deciding whether to quarantine them or not quarantine them. You're deciding whether to, you know, back in the days right after 9/11, people would show up at the airport and you'd get pulled off in the little room. And those were based on these kinds of models as well. So these are used all the time, these classification models. So, I'm going to look at precision recall curves. Okay. And over here, I'm going to do recall. And up here, I'm going to do precision. And what you're going to find, this is going to be 1 and 1, because these are rates. And you're going to get a curve that looks very much like a flipped over ROC. Okay. And so this would be bad. This would be better. Okay. So you choose the classification procedure that gives you the most bowed out precision and recall curves. But there's a problem with that. And let me point out one of the problems. To the lady who said, you know, is this just theoretical stuff or is this actual? Well, this is theoretical stuff. Let me show you what actually happens. This is due to my old colleague, Charles Elkin. Okay, and here's one. Here's one. Okay, and we had that, and I'll do it in green because I don't want people to really see it. So we have a curve like that. Well, oftentimes you're going to get a curve that looks like this. That is, you're not going to get something that's concave. Even worse, you can get this kind of thing. There's one. There's the other. Well, which one is better? Well, this one's kind of better here. This one's kind of better here. You know, maybe you do some linear combination of the two or some average of the two. When you actually look at these precision and recall curves, and this is also the case with ROCs, if you actually calculate those ROCs, oftentimes they just have really bad patterns, and you go, well, this is absolutely useless to me. So it's a little bit disingenuous to say, use the procedure that has the precision recall curve that's the most bowed out, or the ROC that has the area under it closest to 1, because these things may cross over one another. You may have 2 of them have areas under them that are equal to 0.9 and they cross. So oftentimes what people will do, and this is getting pretty close to the correct answer, but not quite there. They will look at the F-score. And what is the F-score? The F-score is 2 divided by 1 over precision plus 1 over recall. And that turns out to be 2, the P times R over R plus or P plus R. P times R over P plus R. Okay? So it's essentially a geometric average of precision and recall. And so oftentimes people will choose the classification procedure that has the highest F score. And there are all sorts of F scores. There are F1 scores and F2 scores and that sort of thing. But they're all some sort of geometric average of the precision and recall. So that's close to the right answer, but it's not the right answer. Okay? What is the right answer? Okay. Well, what we're going to do is we're going to talk about decision theory. Okay. That is, what I'm going to do is I'm going to assign to false positives and false negatives, I'm going to assign a loss or a utility. Statisticians tend to use use loss and do loss minimization. Economists tend to do utility, and we do utility maximization. I will do the utility form of this. I think I'll give you a reading that does the loss. How do you go from one to the other? Well, you just take minus the utility and you have a loss. You take minus the loss and you have a utility. So loss minimization, utility maximization. So let's set up the decision problem. Okay. So I have Y is an unknown state of the world. You're a defaulter, you're not a defaulter. I don't know what it is. You may not even know what it is. You know, it is oftentimes the fact that people who are defaulters didn't intend to default. They're not necessarily bad people, they just end up defaulting. So they're not necessarily criminals. We have probability of Y given X is, of course, the probability of Y given X. And we know how to estimate those now. That's what all this estimation of probabilities was about, was estimating those probabilities. And now I'm going to have U of Y in A. And this is the utility of it's the utility I get, or the loss, if Y occurs when I choose A. So I'll say if Y occurs and I choose A. What would A be? Give you a loan, not give you a loan. And oftentimes they're done in the same I'll say terms as Y. So Y is defaulter, not defaulter. A is say you're a defaulter, say you're not a defaulter. And if I say you're a defaulter, you don't get the loan. If I say you are not a defaulter, then you do get the loan. And so the action is implied by the prediction. But that doesn't always have to be the case. And then we have the expected value of U of Y and A given X. Okay. So given an X, what's the utility, the expected utility you're going to get if you chose A? Okay. So Y is a random variable, X is fixed, so I observe some characteristics from your loan application. From that, I estimate the probability you're a defaulter. And then I say, what is the expected utility if you default? And we're going to call this R, A, and X. Okay? And so if we have this, and let's forget for the time being how we define this utility, oftentimes it'll be something as simple as profit, or it'll be minus a loss, something measurable. It won't be utility in the utility theory sense, but it could be as well. That's in fact where you get the F score. The F score I can show turns out to be something like a Cobb-Douglas utility function with coefficients half. So what is my optimal action? Okay, it's equal to argmax by choosing A, R, A, X. Okay. This is what you learned in utility theory. You choose the alternative that maximizes utility, that makes you the best off. Now, what do I have in here that I didn't have in before? I have this utility. I'm now requiring you to say, if it turns out that you're somebody's a defaulter and I've chosen the action that assumes she's not a defaulter, what's the utility? What's the loss? Maybe what's the profit or negative profit? Okay. So let me put this into a simple framework. So I have the state Y, I have the action, I'll call that Y hat, and I have a 0, a 1, I have a 0, a 1, okay? But now I don't have true positives and true negatives, okay? Instead, I have this. I have, what is the utility if I choose 0 and the state turns out to be 0? Okay. What's the utility if I choose 1 and the state turns out to be 0? What's the utility if I choose 0 and the state turns out to be 1? What's the utility of 1 if the state turns out to be 1? Okay. And so, what did we have? We want R, A, X, I'll call it R, 0x to be greater than R1x if 0 is chosen. So it turns out that this is probability 0 given x times u00 plus probability 1 given x times u01 is greater than probability 0 given x u10 plus probability 1 given x u11. Okay? So this gives me the conditions under which I would choose 0 to classify u as a 0. If it's the other way around, I would classify u as a 1. Let's do a little bit of arithmetic here. The nice thing about this is you literally can sit at your desk, come up with back of the envelope calculations for these things, and say, you know, I think the threshold ought to be, and everybody will go, man, she is a genius. How did she do that? She was just sitting there kind of gazing off into space, and then she comes up with that, and sure enough, she's right. So I'm going to write it this way. So this is u00 p0 plus u01 p1 is greater than u10 p0 plus u11 p1. Okay? And so this implies that u00 p0 minus u10 p0 is greater than u11 p1 minus u01 p1. Okay. This gives me p0 times u00 minus u10 greater than u11 minus u01 p1. Okay. This gives me p0 over p1 is, and we're not sure about this yet, u11 minus u01 over u00 minus u10. Why am I uncertain about that? Well, if this turns out to be negative, then that will flip the sign around. So assumption u00 is greater than u10. Okay? And if that's the case, then we have p0 over p1 is greater than, let me make sure I did that right. Yep. u11 minus u01 over u00 minus u10. You might say, well, wait a minute, where did this assumption come from? This says the utility of getting things right is higher than the utility of getting things wrong. Okay. Does that make sense? Yes. In fact, if it's not true, you have no decision to make. It means that one of the things dominates no matter what happens. Okay? But this is an assumption. By the way, they can't be equal because you got a 0 there then. Okay? And now you sit there and you say, okay, I have an estimate of the probability that the state's 0, an estimate of the probability that the state's 1. I have my loss 1, 1, my loss 0, 1, my loss 0, 0, my loss 1, 0. And I just have back of the envelope calculations of that. And I can tell you then, which one I should choose. How am I doing timelines here? So do I want to? Yes. So I'll end the lecture by taking this back to what's traditionally done, so you can see how this loss stuff is related to precision, recall, specificity, sensitivity, type 1 error, type 2 errors, ROC curves, and precision recall curves. Okay, so 0, 1 loss. Okay, so here's the state. It's 0 or 1. Here's the action. I'm going to call it y hat. It's 0 or 1. Okay. And now what I'm going to say is, if it was a 0 and you predicted a 0, there's no loss. If, or utility, I should, yeah, let's 0, 1 utility. And it's 0 minus 1 utility. Similarly, if the state was 1 and you said it was going to be 0, your utility is minus 1. If your state is 0 and you said it was going to be 1, your loss is minus 1. And if you got it right, your loss is 0. And so now we have P0 over P1 equals 0 minus a minus 1 over 0 minus a minus 1 equals 1. In fact, I have to be careful here, is greater than, that equals 1. So 0 chosen if P0 over P1 is greater than 1, or P0 is greater than P1, or P0 is greater than 0.5. Why? Because P1 is 1 minus P0. Okay? So the standard way of making these decisions, and it's the one that's in the book, not the decision theoretic, corresponds to the 0, 1 loss. And most of you would say, you know, I don't really believe that. And by the way, this doesn't have to be a 0 and a 1. This could be minus anything as long as they're equal. So it's the losses are equal, and getting things right gives you 0 utility. Okay, that will be it. I will start having office hours this Wednesday. And as I said, it would be ideal if a number of you wanted to get together and say, we have this question, can you talk to us all together? Otherwise, I'm going to have to let you in kind of one after another, and it's not going to be like you're, you know, standing outside my office and all of a sudden saying, hey, that's exactly what I was going to ask about, can I pop my head in? Second thing, and you can answer whoever wants to now, is the whiteboard better than it was the last time?
Yes.
Good.
Yeah, I like it better.
Well, I do too. You wouldn't believe what I did here. I think Fahad is going to give me an award for this. You notice that the camera is up there, right? That's how I got rid of the the reflections off the lights. So I put them up so it's pointing down and you can't see the lights. You can see a little bit of them, not much. What I didn't know when I got this is that there are non-reflective whiteboards. And had I known I was going to be doing this, I would have gotten a non-reflective whiteboard, which is a little harder to erase, but I would have taken that in a minute rather than trying to figure out how to deal with this reflection. So I appreciate your patience with this. I know this is just a royal pain. You know, I wish we could do it better, but you know, it's what's that old book? You know, Love in a Time of Cholera. This is machine learning in a time of pandemic or corona. Anyway, I'll see you all next time, and any of you who want to get in touch with me, please do so. Okay, good night.
Thank you.